of them are kind of intermediate, some of them are very difficult to solve, and some of them can be written as a code, but they won't give you answers for certain types of problems. Okay, yes?
This technique goes over the whole list.
Yeah.
Which is mainly,
Which is mainly?
the speed of speed.
The number of iterations that you execute in the max function here. Okay, so let's get back to it. The number of iterations that you execute within this loop is equal to the number of elements that you have in hand. I totally agree.
What if we sort the list and then just take the last one?
So if we sort the list, if we keep our list sorted, okay, then we can, let's say, imagine the numbers are sorted within this array in decreasing order. Then we can return the first element systematically. And in this case, our algorithm, whether we have 1,000 students, 10,000 students, if we want the student with the highest grade, and the array is already sorted by grade, then we can return the first element in that list. Okay, I totally agree. And this is how we can make certain tricks in our software to make it faster. Okay, this is one of the rules. If you store your data in the way that you want to retrieve it, this is the fastest way to retrieve it. Okay, just store it and then you get a copy of it. You just read it. You don't need to make any calculation on it. Okay, I totally agree. Okay, so is it that easy? So these typical types of problems, such as finding the minimum maximum, searching a list, and computing a certain sum, they are relatively easy. There are other intermediate level programs, such as sorting a list or merging two sorted lists. Okay, so if you have two sections of a certain course and you have the first, second, third in each of these sections, and you want to get the final sorted list of students, okay, by grade, then you have to pick up the highest grade from the first and the highest grade from the second, to compare them, to put the highest one in there, okay? The other one, you keep it in hand and you compare it with the next element from the first list, okay? And so on and so forth. So this is a bit trickier than just looking up in one single list for an item, okay? Searching for a node in a graph, okay? A node that contains a specific value. Let's say you're looking for the, you know, when you send a certain packet over the network, you know that it is going to a certain server in the USA. So you need to check which router is the best router to send this packet to, so that it goes with the shortest path, okay? It's straightforward to that router. Some hard exercises would be to find the shortest path in a graph. Detecting characters from images, which requires what we call machine learning or AI algorithm, or building the final exam schedule for students without conflicts, okay? These are really hard problems, okay? They are hard to solve by like human beings, not with a naive algorithm. A naive algorithm is straightforward. We can solve them with them, but actually it would take years to give you the result, okay? So to solve them in a smart way, in an efficient way, is hard, okay? So writing an efficient algorithm is hard. And this is why we need to study these types of algorithms one by one until we get a experience in how to study the complexity of algorithms. Some other problems, they are hard, they become intractable by machines, so we cannot even solve them. Like we don't have algorithms for them to be solved in reasonable time. And some other, they are simply unsolvable, so they are undecidable, okay? Such as the halt problem, which consists on writing a program that it checks whether your program is correct, okay? We cannot write such a program, okay? And we can prove it with the same trick of Cantor to prove infinite sets, okay? The problem is when you write a certain program, you write a finite set of instructions, okay? Nowadays, even with quantum computers, we won't be able to write infinite programs. It does not exist. You write finite programs, okay? And problems are infinite, okay? So problems that you may want to solve in real life are infinite. You can always find another problem by changing one of the existing problems. It never ends, okay? So with a finite set of instructions, you cannot solve an infinite set of problems, okay? You cannot define a bijection between the set of programs and the infinite set of problems. So this is a very quick proof to show you that there must be still infinity of problems that we cannot solve, okay? And there is a very elegant proof for this in later courses. Okay, let's focus on searching problems and sorting problems right now. Searching consists on finding the position of a particular element in a list, okay? Why is it important? I want to check the grade of a certain student, okay? So I have a database, kind of a table, large table with hundreds of thousands of entries, and I want to look up by ID. I know the ID of the student, okay? It's useless to search by first name. Plenty of students have the same first name, okay? Maybe few of them have the same last name. A couple of them have the same birth date, so we are not sure. So it's better to check it by ID. And once you find the ID, you can go to that specific line and check all the other details, the grade over this course or that course, and so on and so forth. So searching is very important. You do this all the time. By the way, your phone book has these two functionalities. You search for your phone book by name, okay? And you search your phone book, actually you have your phone book sorted all the time alphabetically, okay? So sorting is also very important, okay? If you go to Facebook and you see your feed in a complete random way from 2007 till now, okay? It's useless, okay? You would like to see the last news feeds, okay? So it's sorted by date, for example, okay? We have other types of problems that we do not tackle in at least not in this session. Optimization problems where you want to optimize a certain business process. Let's say you want to, it's like the problem of the knapsack problem, where you want to collect the maximum items with the highest values, but that you can afford with you, okay? So let's deal with search problems. We're gonna apply it on numbers. We're gonna consider a finite list of numbers, A1 to AN, and we want to find a specific item X in that list, okay? Typically we call it a key, okay? So we want to find a certain key in a list or sequence of keys. So example, a library might want to check to see if a student is on the list of students who with overdue books before allowing him or her to check out another book, okay? So I gave you a quite similar example for checking students' grades. So the solution to a searching problem, so I mean the function that you would define that is called search must take in the array of or list of values the key that you want to search for, okay, or the value that you want to search for, and then it must return the position of that value in your array, okay? Because given the position, you can go and get other information, okay? So we will study two different algorithms, linear search and binary search. Linear search work for any types of arrays, okay? But it is not that efficient, but it is the only way to do it, almost. And you have binary search, which only works with sorted arrays, okay? It's related to the suggestion of Ali a few minutes ago, okay? When he wanted to check the max, okay? So he could go and return the first element if the array is already sorted, okay? Very smart. So, good. How linear search work? So, can anyone explain this to me? Yes? Yes. Yes. Okay, so the algorithm, this function or procedure called linear search, it takes in the integer to look up for, the sequence of integers, and it goes sequentially, okay, in a linear way, sequentially one after the other, okay? So to go over all the items, it's gonna define a certain index I, okay? It's gonna start it with 1 to pinpoint over the first element in the array, at the first iteration. And it will check whether x is equal to ai or not, okay? So as long as, so x is given as a parameter, is the value that you are looking for, okay, in the array. So as long as I is less than or equal to n, okay, and as long as x is different than ai, we're gonna increment I by 1, okay? We're gonna look up at the next item in the list, okay? So at the first iteration, we will be looking at a1. I is equal to 1 and 1 is less than n, okay? Suppose n is equal to 10, okay? Then we will get inside this while loop. We will check also that whether x is equal not to ai. If x is equal to a1, suppose a1 is equal to 3 and x happens to be equal to 3, then in this case we will go out of the while loop, okay? Why? Because x different than 3 is false. False and anything else is false. So the condition for the while loop is not true anymore. We will get out of the while loop. We will check if I is still less than or equal to the size of the array. It happens that it is still equal to 1. In this case, we will return the location being equal to 1, okay? So it means that, yeah, we found that item, x is equal to 3, and we found it at the first place, okay? Imagine that x is not equal to 3, x is equal to 4, and 4 is the second item here, okay? So let's restart our code execution. So I is equal to 1. 1 is still less than the size of the array. X is equal to 4. It's different than a1. It's not equal to 3. Then this condition, both conditions are true. X is different than a1. X is different than a1. It's equal to 3. It's not equal to. It's equal to 4, not equal to 3. And 1 is less than the size of the array. Then we have to get inside the while loop. We increment I by 1. At this next iteration, I becomes 2. Okay? The code now checks whether 2 is less than or equal to the size of the array. Suppose, yeah, it is still the case. And it also checks whether x is different than a2. Okay? If a2 happens to be equal to the value of x, then we stop and we return it at the location. Otherwise, we continue. Okay? And it goes over and over again and again. Yes?
0 stands for a1.
Where? You mean here? Here?
Index 0 is the first element.
No, the first index in this array is 1. Okay? So in this algorithm, the first index in the array is 1. And 0, it means that your value does not exist in the array. Okay? The x value is not, it does not exist in the array. Okay? Good. So whether it's equal to a specific index or equal to 0, it means it does not exist, we return it anyway to the caller.
Is it 0 position in the array?
0, it is a position that is outside of the array. Okay? So it has been explained here. So the solution to a searching problem is the location of the term in the list that is equal to x. That is, it's the location number I if x is equal to a number I, for I equal 1 to n. Otherwise, it's 0 if x is not in the list. Okay? Yeah. And most programming languages, so your colleagues are asking about this specific issue, because in most programming languages, arrays are defined with the first index being 0. Okay? The first element in the array is a0, the second element is a1, and the last element of the array of size n is index n minus 1. Okay? So in this case, we would return -1 to tell the caller of this code that the element does not exist. Okay? Because -1 is an invalid index in the array. Yes? Sure. Yes, we could solve it with a for loop. Yeah, I totally agree. Okay, so for I equal 1 to n, except but it won't be the same. It won't be the same code 100%. Okay, this code this code specifically returns the first position of the first element that is equal to x, okay? Actually, the position of the first occurrence of x within the array. If x happens to be multiple times in the array, it won't be returned. Using a for loop, since you will iterate up until the end of the array anyway, then you will be returning the last index of the element in the array, okay? But so this is why the result will be slightly different. If you use a for loop, but you allow yourself to use the break statement that we don't learn in this course, okay? There is a statement called the break that you can write within a loop to say that if you have this condition satisfied, then break the loop and go outside of the loop, no matter what the condition, the initial condition of the loop. So, by the way, if you can write while true, usually this is an infinite loop, while true, do this, do that, and if you have this, then a break, okay? So you could replace the condition that is written within the while loop, you can write it inside an if statement and use the break statement inside it. So if you use a for loop and you want the same result like here to stop at the first occurrence of the variable within the array, then you have to say if the variable happens to be equal to AI, then break, okay? Just to go outside of the for loop, okay? Good. This is the complete answer to your question. So here you have the an example of how this runs. So I think I already clarified it to you. So since we are looking for x equal to 6, we will find it at this place, okay? We will return finally this position, I is less than or equal to n, but and this is a valid location, okay? So this is why we return finally 4 as the location of the item within the array, okay? Good. What if x does not exist in the array? So what if, let's reconsider this value here, this array. What if x is equal to 64? Yes. Yes.
Can we, instead of assigning a value of x, we put a condition of an x to take it as a round?
Yeah. So, of course. So the question of your colleague is, could we look up for a value that meets a certain criteria, that is not equal to a specific value, but that meets a certain criteria? I agree with you, but the only problem here is that this criteria cannot be passed as a parameter, okay? So don't forget, we passed the value that we want to look up for as a parameter, okay, to the function. Let me show you the code. So the exact value that we want to look up for, we pass it as a parameter, okay, to this function. It is quite difficult to, actually there is a way, but it's complex. We don't learn it in this course or pseudocode to pass the criteria as an argument and not the, okay, and not the variable itself. It can be done actually by passing called meets criteria x, okay, and you can apply actually this function called meets criteria as x within this instead of this test here, because your criteria is not anymore x different than AI, okay? It's I don't know, it's a function that check x in a certain way, okay? Good. So you pass to that function the variable AI, and it works that way. If you want to fix the criteria, if you don't want to pass the criteria as a parameter, you can fix it. You can put like a criteria such as the absolute value of AI is equal to 32. Okay, so whether it's minus 32 or 32, you accept it. Okay, so you can put whatever you want, of course. Okay, but let us check if we are looking for a value that does not exist in the array. What would happen? So we will continue up to I equal to 10. Okay, so for I equal to 1, 10 is not equal to 64, 15 is not equal, minus 8 is not equal, and so on and so forth. And then we will check 12 at the end. For I equal to 10, it's not equal to 64. We will increment I, we will go out of this for loop, okay? And we will come to this check, to the check that we have here, okay? If I is still less than or equal to n, I is equal to 11 now, okay? It's strictly greater than n, which is equal to 10. Then we will go to the else statement and we will put in the location 0. It means that my variable or my value does not exist in the array, okay? Okay, how many iterations we have executed so far when the value does not exist in the array? 10 iterations, okay? So 11 iterations specifically, so n plus 1, okay? So if you have 10 values, then we would have done 10 iterations. If we had 1,000 values in the array, then we would have done 1,000 iterations, okay? 1 billion values, then we would have done 1 billion iterations, okay? So, and this is why it's called linear. It's not because it goes sequentially over the values, but because the complexity of this algorithm is linear. It's to the order of magnitudes of the function y equal f of x actually, and it's equal to x, okay? So for n values, you need n iterations, okay? The needed time, the needed number of instructions is equivalent somehow to n, okay? It's like the curve y equal to n. Good. So what if our list of items is sorted? Can we do better? So we can use the same algorithm and we will get fantastic results, but we will have the same complexity. It is a linear time. We need that much time. For 1 billion records, we need to do 1 billion instructions, okay? Good. But can we do it in a smarter way? Do you know, who knows about binary search? Okay. All of you? Good. So, can anyone explain it to me? Yes?
So you take half of the array. And
So we go to the middle of the array, yes?
you evaluate.
Okay.
If it's greater or smaller.
Okay, I'm looking for x, okay? The array must be sorted. We highlighted this fact, okay? So the array must be sorted. So we go to the middle of the array, okay?
Then you break the array.
Absolutely. So if the value in the middle is greater than the value that you are looking for, suppose your array is sorted in increasing order, okay? If the value that you are looking for is greater than, then it must be in the second half of your array, okay? Otherwise, it must be in the first half of your array. The ideal case is to find it right in the middle, okay? Bingo, you solve it in one step. But in the worst case, even if it is not in your array, okay? When you throw out half of the values, imagine you started with 1,024 values, okay? You will see that you will only need 10 steps to solve this problem. You can play this game with your little brother or sister and ask them to pick up a number between 0 and 1,023, okay? Or 1 and 1,024. And you make the bet that you will guess the number in 10 steps, okay? Ask them to write the number on a piece of paper and don't look at it. You can't do it. They have just to be honest with you and to tell you whether the guess that you made is greater than or less than. And go always with the middle, okay? So give them 512. If it is bigger, then the next time go to the number between 1,024 and 512. If it is less, then go to 256, which is the middle of the values between 1 and 512. Next time you will go to 127, if it is smaller, then 64, then 32, and then you will get to 1, okay? If it is number that is outside of the scope, then if they are cheating, then you will always guess it within 10 steps, okay? Anyway, okay? And why this number 10? What is the relation between 10 and 1,024? Because 1,024 is equal to 2 to the power 10, okay? So, and in this case, 10 is the logarithm of 1,024, okay? It's the number that, okay, logarithm base 2, okay? It's the number that if we raise 2 to it, then we get 1,024. And the logarithm is something that drags down the values. It's a very soft curve, okay, that go asymptotically to the x-axis, okay? It goes very slowly with the x values. It does not increase steeply, okay? So this is why instead of solving your problem in a linear time, This is the function y equal to n, okay? You need n iterations for n inputs, okay? So if you can solve it in log of n, then you would solve it very quickly, okay? And this is what is nice with binary search, okay? So technically, the idea is good, is brilliant, but how to code it? So let's take a look at this. So we have a value that you want to look up for in a certain array of n values. So we will consider two different variables. I would call them start index and end index, okay, without putting any command beside them, okay? So look at this approach. We always have to use a command to tell what these I and j's are doing, okay? So if we use clear variable names, start and point and start point and end point, or left and right, or any other clear name, then we would get rid of these comments. So while the start is strictly less than the end index, while the start index is strictly less than the end index, okay, because at a certain moment they will overlap, okay? So we will start with the start index being equal to 1 and the end index equal to n, to the last item, okay? At each iteration, we will consider the middle. The middle index is equal to the start index plus the last index, the end index, over 2 floor, okay? Just to make sure that the index is a valid index. It does not have 0.5 in it, okay? And it's not a big deal if you go one step further or one step later, okay? So we'll go to that element in the middle. So we check with a index m, a that exists in the middle of the array. If it is less than the value, actually, if it is equal, then we should return it right away, okay? We should return the location m. If x is strictly greater than that value, then we put in I m plus 1. Why? Because we want x happen to be greater than the value in the middle, and the array is sorted in increasing order. So if x is greater than the middle, then it's necessarily in the other half of the array, okay? So we will push the start index, which is I, to the middle plus 1, and we will keep the end index, j, at the same position. And now when we will go to the next iteration, we will update m with the new value of I plus j, okay, the end index plus start index over 2. We will go to the third quarter of the array, okay? It's the middle of the second half of the array. Otherwise, we will put in j the value of m minus 1, okay, or m, okay, just to pick up the first half of the array, okay? So this is called the concept or principle of progressive halving, okay? And if you are dividing all the way by 2, so you will end up with a logarithmic algorithm. So is it clear how to proceed with this? Yes?
Why the as j equal m, not x less than 8m, y equal m minus?
I agree with you. It's a tiny bug here. So because with else it means that x greater than or of am is false. And in this case, it means this is equivalent to x less than or equal to am. And when it's equal, we have to return the index m right away. So I totally agree with you, okay? So we had to retest once again whether it's strictly less than, okay? Because when x is equal to ai, when x is equal to ai, we have to return that location and the problem is solved, okay? Personally, I would put this instruction at first. If x is equal to am, return I, the variable, okay? Else, if it is strictly less than, do this. Else, and in that else, it will be the otherwise of both cases. It's not equal, it's not strictly greater than. It means it's less than, okay? Good.
Can we just repeat the step?
Sure. So I think we have an example here. Please, guys. Guys. Okay. So let's consider this example. We want to look up for the value 19, okay? And we have this, I think, 16 values array. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't have all the values. So I think yes. Okay? So we have 16 different values and 12 is in the middle. Okay, guys? I think 16 and 12 is the 8th element in the middle. Okay? So if you want to look up for this value, we go anyway to the middle. Okay? We can apply binary search, by the way, because the array is sorted. Okay? It is sorted in increasing order. So you check the 8th element, actually, sorry, the 8th element happens to be 10, okay? The 8th element is 10. And 19 is strictly greater than 10, okay? So in this case, we have to update the value of I, the start index of our search space, to become the 9th element, to become the middle element plus 1, okay? And we keep on the end index at the same position, okay? So the new I and the new J are these values here, okay? So if X, look at the code, if X is strictly greater than the value in the middle, then we update I, okay? We put in I the middle plus 1, okay? So now we have this array, we have to go to the middle of it. So the index, which is 16 plus 8 over 2, it must give us something, 9 over 2 floor. So it's 4 plus 16 is equal to 20. So we must go to the, 12. So we must go to the 12th position, okay? Which is the value 16, so here, okay? So 16, is it greater than or less than the value that we were looking for? It's less than. Then it means that our value must be in the last half of the array, okay? Which is from 12 to 16. So this is why we update the value of I to pinpoint towards this value, 18, okay? And we keep on J at that position here, okay? We go one step further, we will look up inside this array. The middle of it happens to be 18 because we are taking the floor of the middle. And then finally, we'll find our value here. If your value was, let's say, 18.5, then you won't find it in this array. Okay? But anyway, it won't take you more than these number of steps. Okay? Yes?
So if we change the problem a little bit,
Yeah.
say we want to insert a new number in the list.
If it does not exist, yeah.
If it does not exist, and do it in the fastest way possible.
Yeah.
Still,
the same way. So you use binary search to locate the position where you have to insert it. If you find you don't want to duplicate it, then it's fine. Otherwise, you can copy the next elements one step further and free a certain space to insert your element there. Okay? Good. Let me check. Okay. If you grant me, is it fine for binary search? Is it fine? Okay. If you grant me just 10 additional minutes, I can give you the first types of sorting algorithms. Okay? The first types of sorting. I know that most of you know already how to do sorting, and it's not that difficult. Okay? So. Sorting is one of the most studied problems in computer science and in programming specifically, okay? Because with sorting, like already with searching, we scan the whole array if the array is not sorted, okay, to locate a certain element, okay? To sort the array, we need to do multiple passes actually, okay? Precisely 2 passes in general, okay? So nested passes, I mean, okay? So if I have a set of students, let's say, okay, I have to ask one of them about his or her height, and then I have to compare it with all the others, okay? And I have to make sure that the first time I'm doing this scan for the whole class, I'm picking up the minimum, okay, height. I'm asking the student to come and to stand here, and then I have to reiterate for the whole class once again, okay? So sorting can use the same spirit of the min or max functions, okay? But you have to do it again and again and again and again, okay? So if you pick up the maximum, let's say, or the minimum of the whole array from A1 to AN, and put it at the first place in your output, okay? Then this is the first step of your sorting algorithm. What you can do, you can pick up the minimum out of your whole array minus this minimum here, okay? So you have to take out this minimum and to look up inside the remaining values to pick up the minimum out of them and to put it in the second rank. And then you continue this way, okay? Each minimum requires almost n iterations, okay? It's not really true. The first time when you calculate the minimum of the whole array, how many iterations do you need? N iterations. When you end up with n minus 1 items, you want to calculate the minimum out of them. How many iterations does it take? N minus 1, okay? And so on and so forth. At the end, when you end up with one element, it is absolutely the minimum of the remaining list of items. So you will just copy it. It will take only one iteration, okay? But we already know, and we have proved with induction, that this is equal to, okay, so it's equal to n times n plus 1 over 2, okay? Which is something to the order of magnitude of n squared. It's true that it is n squared over 2, okay? But it really hurts. Why? Because why are we interested in the order of magnitudes of things? Because if you have 1,000 students, okay, picking up the one with the highest grade takes only 1,000 steps, even if the array is not sorted, okay? It's a linear function. If you want to sort this array, it takes you 1 million iterations, okay? Even if it is 1 million over 2, okay, somehow, but it still hurts, actually, okay, in terms of time, required time to execute it. Imagine that you can solve 1,000 instructions or iterations in 1,000 milliseconds. 1,000 milliseconds is equal to? So 1 second. But now to sort the array, you would need 1 million milliseconds. It means 1,000 seconds. And 1,000 seconds, it's almost 20 minutes, okay? So this is why certain badly written algorithms takes like a lot of time, or you find that the software is not very well done, okay? So for specific cases, they work fine, but once you exceed a certain threshold, you will find a very bad performance, okay? Good. So this is why we're interested in tackling this problem. And it has been tackled in hundreds of different ways. There are tons of algorithms about sorting. We will learn only 2 algorithms today, okay? So the algorithm is as follows. It consists of sorting a set of incomparable items, typically integers, okay? But it can be anything comparable, okay? If it is not comparable, you cannot sort them, okay? So you have to define a certain criteria to compare the items and to sort them. And the output is a certain permutation or reordering of the items so that according to your comparison operator, the first item is less than or equal to the second one, and so on and so forth, up to the last one, okay? So it can be alphabetical order for names, it can be normal order for numbers, and so on and so forth. Good. So why do we study it? Why do we study different sorting algorithms? So I already give you the idea behind it when I studied the complexity of it with you. So because it is quadratic, it is not linear, then it takes a lot of time. And we do sorting so often, all the time. Okay, we do it regularly in all types of software. So your WhatsApp messages are sorted all the time by date. Okay. The way they are stored in memory, it's kind of random, okay? But they sort them before displaying them to you, okay? So you do sorting all the time. So we study different sorting algorithms or techniques because sometimes certain sorting algorithm works well when the array is pseudo-sorted, okay? But some others performs better when the keys or the values in your array are not sorted at all. They are randomly positioned, okay? If all the keys are distinct, certain sorting algorithm can do better in these cases, okay? And how large is the set of keys to be ordered, okay? This really influences the final outcome. And we need to guarantee a good performance in average over all these sorting algorithms. So you will see that the complexity is to the order of n squared. I will explain this notation starting next week. Okay, it has the order of magnitude of the curve of n squared, but we can get better performance. Okay, so we can get down to n log ln. Okay, n times log n, which is much better than n squared, because log of n is better than n, so n times log of n is better than n times n, okay? Okay, so let's check this naive algorithm, but it's a very funny, very nice algorithm called bubble sort, because the designer of it visualized it in this way, as if the values were balloons with different volumes of helium, let's say, okay? And the more you have, the lighter the balloons, the higher they will fly, okay? And the lighter the balloons are, they will come to the first places in the array, okay? They will not fly that high. So how it works, look at the lines of code. They are just 3 lines of code. So it will go from the first element up to the before last element, okay? From the first to the before last element. And you will use another index, okay? You will use another index to compare actually all the elements up to n minus I, okay? So at the first stage, you would go to the almost last element, before last element, okay? Next time, you would reduce the scope and so on and so forth. And what you will do, each time you find 2 adjacent values, aj and aj plus 1, okay, 2 successive elements in your array, you will compare them. And if you find that the element to the right, okay, the balloon to the right is heavier than the balloon to the left, okay, you will swap them. You will interchange their places, okay? So you will swap them. So at the first pass, imagine what we are doing. So let me consider this array. So very simple one. I have 1, 3, 2, okay? At the first pass, I will compare 1 and 3, okay? 1 is it greater than 3? No, so I won't do anything. Then I will consider 3 and 2. Is it the case that 3 is heavier than 2, greater than 2? Yes, then I will swap them. So I will end up with, so I'll make this exchange and I will end up with 1, 2, 3, okay? But you have to continue anyway, because we are not sure whether we have, let's say, another one here, okay? So suppose we have another one. After swapping these values, okay, we will end up with, we have to swap 3 and 1 once again. We will end up with 1, 2, 1, and the 3 because we swapped 1 and the 3. But our array, so the heaviest balloon is to the right hand side, okay? It is at the right position. So after the first pass, the heaviest balloon is to the right hand side. It is at the right place. But the remaining part of your array, it is not guaranteed that is already sorted, okay? Just because you did the swapping locally between two adjacent elements, okay? Yeah, no problem. It is still sorted in this case. Yeah. Yeah, it must be this way, okay? Okay, yeah. One question. I had one question somewhere. Yeah. The first loop, so imagine that I have only this inner loop, okay? Imagine that I fix I equal to, actually I'm not using I inside in the inner loop, so forget about this one for just one moment. If I'm just doing this pass, okay? Imagine that we had these values here. So for j equal 1 to, let's say, to n, not to n minus I, okay? Just to n. If I'm doing this, I'm swapping the values in case the value to the left is less than the value to the right. Then after the first pass, I will end up with, okay? So I compared 1 and the 3, I didn't swap them. 3 and 2, I have to swap them, okay? Then 3 and 1, I swap them. I ended up, after this whole iteration, after considering all the numbers, with 1, 2, 1, 3. Yeah. We need to continue because, sorry guys. So after making this first pass, okay, over all the items of the list, we are just sure that the highest element is on the right hand side. It's at the end of the array. But we are not sure, we don't have any information about the order of the inner array.
Why did you do it only one time? The inner loop only do the aspiration one time. So you add the upper loop.
I didn't get your point.
He's asking if the second loop performs just once again. It moves each index, it compares them and just moves them, then moves them and moves them and it stops. But there's no outer loop. The outer loop ensures that
it goes back once again, okay? Yeah.
So the index, why would the index, why would I come to the second pass?
Yeah. Yeah, because at each iteration, okay, you are sure that the heaviest balloon goes to the end of the array, so you don't have to reconsider it once again. It's useless to reswap it once again, okay? We could fix, actually, it's a very nice question. We could fix the indices. We could consider for I equal 1 to n, just do the inner loop n times, okay? And we could take the inner loop from 1 to n, and this won't alter the final result, okay? Subtracting I from the inner loop and taking the outer loop just up to n minus 1 is just a kind of optimization to the number of iterations. It's a tiny optimization. But if you do it n squared times, okay, and you compare all the way, all the time, all the values, then the same algorithm works very well, okay? Just in a few cases, in a few algorithms, you have to do such adjustments, okay, to avoid re-randomizing the array after sorting it, okay? But in the bubble sort, if you check all the time, you see yourself doing after the, let's say, the iteration number n over 2, you will be doing n over 2 useless operations to check the values that are already sorted at the end of the array, okay? So this is why we limit the j index up to n minus I, okay? And we do not continue up to the end of the array, okay? Yes?
So this is essentially moving the
Yeah. Yes, yes, and just forgetting about it, okay? And so to tune this, okay, we have to repeat it n times, but not necessarily n times. You can do it only n minus 1 time, because the last element, the lightest bubble, will be at the first place by the end of this algorithm. So we don't need to do it n times. And this tuning here, because all the elements at the end of the array would be sorted after the iteration number I, okay? Yeah? Yeah, if you want to refer to I, then you need to do these tunings also, okay? Just to make sure that the indices are correct, okay? So here you have an example of how this algorithm runs, okay, on the original array. We will be using this symbol to say that we have an interchange, okay? And we will use this symbol to say that the pair that is considered, they are in the right order, okay? So at the first pass, we have to swap 3 and 2, because 2 is lighter. So the bubble 2 is lighter, so it has to go to the top. 3 and 4, they are at the right place, so we can keep them. 4 and 1 is lighter, so it has to go up, okay? 4 and 5, they are in the right order. But we need the second pass. In the second pass, it's useless to go to the last step, because we are sure that the heavier element, which is 5, is at the bottom, okay? So we compare 2 and 3. 2 is at the right place, no swapping. 3 and 1, we have to swap them. 3 and 4, they are at the right place. So we end up with this configuration here. We are sure that the heaviest element, next heaviest element, which is 4, is also at the right place. So we only consider from j equal 1 to n minus I, okay? So 2 and 1 is lighter, so it has to go up. 2 and 3, they are at the right place, so we do nothing. And in the fourth pass, anyway, we check 1 and 2 just in case they were not in the right place. And that's it. We conclude we don't need to go for the last nth iteration, because when 1 is left on the top, we are sure that it is the lightest element. It is the smallest element, okay? And this is how bubble sort works, okay? We have another version called insertion sort, and you have a couple of other algorithms such as selection sort. We will learn about merge sort later on, but it's enough for today.
Are we going to do insertion sort now?
No, later on. Thank you.
Thank you.